All right. Good afternoon. Can we start now?
Good afternoon, sir. Yes.
Right. So let me just quickly summarize what we had discussed about stationarity in the last lecture, and then we proceed ahead. So precisely what we understood was that whenever we have a time series data, the first thing that we should check for in the data whether the data is stationary or not. And by stationarity, what precisely we mean is, whether the data is covariance stationary or not. And covariance stationarity is also referred to as weakly stationary process. Now, the conditions are, very much that the first and second moment of the distribution for whatever variable that we have in front of us, it must be independent of change of time origin. So, if you logically, if you think, what it entails saying is that if you have y and if you have t, and suppose just hypothetical, this is the distribution that you have. So, saying that this is from t naught till this is till tf. This is the sort of distribution that we have for this particular variable. So this imposition of covariance stationarity, what it means is that, whether you're talking about for the time interval t naught to tf, or, for some other time interval, it's a tf plus h to some other, interval. Precisely the mean and variance of the variable that we have, that is of the observations that we have in front of us, this must not change. That is, if you take this, distribution, you place it on some other interval for the same observed variable, the distribution as far as the second and the first moments, that is your mean and variances, obviously autocovariances, it should not change. And that's why the last condition that we have had, expected value of yt minus mu, yt minus s minus mu, this is equal to yt minus j minus mu, minus mu, and yt minus j minus u. So what it says is that, if you have some covariance obtained between, let's say, T4 to T7, and the stationarity requirement is that the covariance will only depend on the lag between the observation. So no matter you place this observation for, some time period before it or for some time period ahead of it, any lag-free autocovariances for this observed variable at whatever time interval you are trying to portray, this will not change. And same thing goes for the mean and variance as well. And this is how we impose this condition of stationarity on time series variables. One more thing that you should generally think of time series as that the time series observations lack this replication, because when we study OLS, what we generally say is that for one x you have normally distributed y variable. For one x you may get plenty of responses, and the responses of y more or less looks like a normally distributed random variable. But this is not the luxury that we have in time series observations as far as such sequence are concerned, because for each of the time period, if you're recording the variable, if you're recording the observation on that variable, that is just a single outcome, a single realization. So it does not happen that you have 1,000 GDP values for one particular year, and then out of that you select just one point. It's not like that. You just have a single observation for each of the year, and that's why stationarity assumption is very, very much important for time series observation, because more or less it makes it possible to generalize or to predict or forecast about the observed variable for some future time ahead, on this basis that the distribution of the variable will not change. That is, it is independent of whatever time period for which you are trying to observe the variable. So this lack of replication in time series variable is being precisely met by imposing the stationarity assumption. And stationarity assumption is precisely that your mean and auto covariances of the time series or of the variable under consideration should be independent of or should not be affected by any change of time origin. सो जो आप मीन एंड वेरिएंस इस पर्टिकुलर ऑब्जर्व जो आपके पास डेटा है उसमें जो आपको मीन एंड वेरिएंस ऑब्जर्व हुआ है उस पर्टिकुलर वेरिएबल के लिए, नो मैटर यू शिफ्ट दैट टाइम पीरियड पीछे या आगे, दैट डिस्ट्रीब्यूशन विल होल्ड इवन इन दोज टाइम पीरियड फॉर विच यू एक्चुअली डू नॉट ऑब्जर्व द डेटा. So this is what stationarity actually means in time series, and almost all the models that we have, the examples of the linear model where we study AR, MA, ARMA, ARIMA, all these models can only be estimated for a variable which is a stationary variable. अगर आपका stationary नहीं है तो first thing we need to make the variable stationary. That's how the process goes. Now, we had talked about three of the tests, or the first particular test is your graphical method. That is, you simply plot the time series and check whether there is any trend component or seasonality component there. If there is any, first we try to make that data stationary by various process. Either you detrend it or deseasonalize it. Sometimes applying logarithm also makes the data from a non-stationary to stationary. Then you do differencing. That's a process of what is called as integration. So you difference the data, you difference the raw data one times. If it is stationary, well and good. If it is not, then again you difference it, and then again you check for. So this differencing process is also a measure to remove the non-stationary part of the time series variable. Then second is your plotting the autocorrelation function. It is also called as correlogram. And the idea is that if a time series variable is stationary, and basically this particular concept is based on a stationary time series only, that and the best example of a stationary time series will be your white noise process. So idea ये है कि अगर कोई time series stationary है तो auto correlation function क्या है? Auto correlation function is nothing but your auto correlation at various lags, auto correlation at various lags versus those lags. So you plot auto correlation at all those lags against these lags, and that's how you get your auto correlation function. So if a time series is purely random or white noise process, then barring for the lag 0, all the auto correlation at different lags apart from 0, it should automatically go to 0. That is, it should not be there. There should not be any sort of correlation or auto correlation at any other lag apart from lag 0. But lag 0 is nothing but your variance, so it will always be equal to 1. So that's how we detect whether a time series is stationary or not, by looking at the plot of its correlogram or the autocorrelation function. And generally we proceed that अगर कोई time series variable का बहुत सारे lags पे भी autocorrelation function it does not decay out to 0, or it does not converge to 0, then we then we are able to conclude that the time series variable is non-stationary. And after this, we have some statistical test, and again, one of the most famous tests for testing for stationarity is your unit root test, or it is also called as Dickey-Fuller test. And a simple modification of unit root test is your augmented Dickey-Fuller test. There are other tests like Phillips-Perron test, KPSS test as well to detect for the presence of non-stationary time series. So these are precisely certain tests through which you test whether a univariate time series is stationary or not. And there's this very beautiful command on R, which is your stationarity test function, which is what we'll do in today's lecture, which gives you an option. Either you can, so the default argument of stationary test function is your augmented Dickey-Fuller test. So if you just do not write what type of test you're using, it will automatically give you the results from ADF test. But if you, let's say, wish to test for stationarity by Phillips-Perron test or KPSS test, then you simply mention the test name and it gives you the result accordingly. Now, before doing that, before actually thinking about these tests, let us just for some time being try and find out these stationarity conditions and stability conditions for the models that we actually make, or the ARMA, AR, MA processes that we actually see. Just for the sake of simplicity, because the algebra will get really complex and we have not introduced all those in our time series yet. So what we'll do is we'll just try to derive the stability or stationarity conditions for an AR1 model.
Sir, just a doubt before we continue.
Yeah.
A correlogram, is it like it compares a certain y and yt and it compares it to yt minus 1, yt minus 2 and so on and so forth?
Correct. Yeah, that's the plot of autocorrelations. Yeah.
And so if this is called a correlogram, what is, assume that we have x1, x2, x3, x4, they're all different.
Yeah.
And this is not a time series, this is cross-sectional data. Yeah. And we take all of those plots and all of those correlations. What is that called? Isn't that called a correlogram too?
That is just your pairwise correlation graphs.
All right.
Correlogram is a term reserved for the time, like autocorrelation function of time series variables.
All right, sir.
Yeah. So in order to, so these tests will automatically be, writing a command on R, but just for the theoretical perspective, how these tests are arrived and what are the stability and stationarity conditions for, AR, MA, ARMA model, and how exactly ACF, PACF functions work. So we'll devote 1 hour to, go about the theory portion of it, and then we can, we'll solve the examples on R from the book that I had actually sent you. So let me just, yeah. So what we precisely want to do is we want to find out the stability or stationarity condition for an AR1 model. So if you are actually using an AR1 model, it means what you're emphasizing upon is that the time series under, or the variable under consideration, follows an AR1 process. That is, the successive sequence of observations on Y can be estimated using one period previous lag plus a stochastic error term, which is a white noise process. So this is what we emphasize when we try to estimate for a time series variable using AR model. Precisely for an AR1 model, what we are saying is that we can estimate the current value of any time series variable just by looking at the one period lag value of the time series variable plus a shock plus a random term which follows a white noise process. So this is what our assumption, or you can say this is what we emphasize, that the variable under consideration or AR1 model, when we write it like this, then this is what what we implicitly mention or say that the data generating process for this variable y follows an AR1 process. And if you really want to use this model for prediction or forecasting purposes, then in order to use this model for prediction or forecasting, the model must be stationary, which is also called as stability conditions for these models. And precisely those stability conditions and stationarity conditions for all these linear models, this is what we'll try to understand from. So we'll just derive the AR1 model and we'll simply write the results for ARMA, MA models. That is the stability conditions for all those linear models ahead. Now, one more thing that we must be able to understand, that yesterday we had talked about that if you have a time series variable, precisely there are three components. Cyclical component is there, but since cycles are defined over longer period of horizon, so let us just take seasonal component as far as the components of time series is concerned. So you have a trend component, you have an irregular component, and then you have a seasonal component. Now, the idea is that if the time series under consideration is a variable where these different components are additive in nature. Additive in nature means that you can decompose the entire time series into these various components and you can simply add them to get you the final value. Such type of models are called your additive models. Basically, the logic behind is this, that if you have a trend component or a seasonal component, which imparts, because we can't do anything about the irregular component as yet. So if any of these three components also varies with the level of the time series, and by the level of the time series, I mean to make you understand that, is it that the seasonality component also varies with respect to time? In the initial period, the seasonal factor is not that much, but when the time series progresses, when you come to the later part of the observations, the variability of the time series also increases accordingly. So in that case, what we are able to conclude is that seasonality is just not, seasonality of the time series under consideration is also dependent on the level of the time series. That is where you are actually measuring that time series under consideration. Similarly, if your irregular components, if precisely the variances of these irregular components also changes with respect to level of time series, with respect to level of the time series under observation, in that case, assuming for an additive model mainly does not work. So in that case, what precisely we have is called as multiplicative model. So that will look something like this. This looks like this. Yeah.
So could you please repeat this last part?
Yeah. See, additive model is what? अगर ये आपका time series variable है, additive means you can simply decompose the entire time series into three separate parts, if these are the three components, and you can get your original variable. Multiplicative time series will be this. That is, you cannot simply add up the components and get to the actual value of the series under observation, because these components, these decomposed components of the original time series, they themselves depend where you are actually observing that those components, and it changes with respect to time. That's why it becomes multiplicative in nature, and the model that we have for such kind of time series is called they are called multiplicative models. And when you have the components which are simply additive in nature, they are called as additive models. Mostly, as far as our course is concerned, or what our syllabus prescribes, or at least as far as the post-graduation first semester is concerned, we'll mainly be dealing with the additive models. Once you go to advanced econometrics and financial econometrics, next semester, then you actually read about the multiplicative models over there.
So,
yeah.
Are I, S, and T, are the three of them any specific things or just random variables you've taken?
This is irregular component of the time series. This is the seasonal component, and this is the trend component.
Trend. Okay. IST. Okay.
है ना?
Okay. Thank you, sir.
All right. So जो भी हम टेस्ट करेंगे, जो भी हम मोस्टली मॉडल्स रन करेंगे, they all are examples of linear and additive models. And wherever your seasonal component or such different decomposed components of time series also changes with the level of the time series, all the models that we read as far as linear models or additive models are concerned, they'll not work over there. So but just to give you this information, that we'll be mostly talking about additive models, and also the tests which are there for running these models, they are also valid only for the additive models. So this point you must always keep in mind. And what is exactly additive and multiplicative models, that you should also keep in mind. Multiplicative model इसलिए क्योंकि जो आपका changes, जो decomposed part of components of time series है, they are multiplicative in nature. That is, they just get bigger and bigger, or they changes in their size as time progresses. Whereas in the additive model, these decomposed parts, they do not depend on the time series or the time period under observation. That's why you can simply add them up and get to the original series. All right. So yeah. So now let us talk about the stability conditions for AR1 model. But एक चीज हमेशा याद रखिएगा कि अगर आप किसी भी वेरिएबल को AR1, AR2, MA1, MA2 मॉडल से एस्टिमेट करें, इट मींस यू आर saying that the data generating process for the time series under observation follows an MA or an AR process, and since you want to forecast or you want to predict anything based on the model, you want your model to be stable, you want your model to be stationary, and precisely what we intend to find out here. So our AR model can be written as so this is your current value of y, this is one period lag value of y, and this is an error term which is a white noise process. White noise process, इसमें आप normal distribution add कर दो, so this becomes a Gaussian white noise process. Now the idea is, how do we exactly find this? So and this is also an example of difference equation, the special case of nth order difference equation that we had talked about in the last class. So this is just one example where the lag or the order of the difference equation that we have taken is 1, meaning which we have just taken one lag to explain or to estimate or to interpret to get the current value of y. Now let us say for the time being you are given an initial value, or let's say first value of this sequence of time series observations, and let's call that value as y0. So this is your initial value. So given y0, I can find y1, that is next period value. Now once I have got y1 by the same relation, I can also find y2. And y1 को यहाँ पे मैं रिप्लेस कर दूं, जहाँ पे भी प्रॉब्लम लगी please interrupt me there. So I can write this now as A0 so this becomes my y2. Similarly, y3 ko I can write A0 plus A1 y2 plus E3. and I can replace this y2, or I can substitute this y2 here, not replace actually. So if you expand this, so this becomes your y3. Now you can keep on iterating. So this is called solution by iteration. That is, you are given one initial value. On the basis of that initial value, initial condition. That is, you have been given that there is a time series sequence, jiska pehla value is given to you, and that sequence follows process. That is, you can get each successive values of the sequence by this model or by this process. So I can get y1 from y0, I can get y2 from y1, I can get y3 from y2, I can similarly get y4 from y3, and so on and so forth. But we did not go much far ahead because we can easily find out a pattern over here. You can notice that y1, here you have a1 times y0. Then again, when you expand this a2, what you notice is you have a1 to the power 2 times y0. So when you are at the first observation, you have a1 to the power 1 y0. Similarly, when you are at the third observation, look at this term, you have a1 to the power 3 y0. And if you go in this manner for the next t observation, or for the next t time period, you can easily find out that this term, there will be a term in the final which will look like this. Okay? So this is one pattern that you can easily find out from this iteration. One next pattern that you can find is that in the first observation you have a0. In the second observation, that is second sequence, you have a0 plus a1 times a0. In the third part, you have a0 plus a1 times a0 plus a1 to the power 2, that is a1 squared times a0. Now you can easily verify in the fourth observation, I'll have a1 to the power 3 a0, fifth may a1 to the power 4 a0, and so on and so forth. So for the tth observation, it will be a1 to the power t minus 1 a0. And I can easily find out that this pattern can be written as a0 summation goes from 0 to t minus a1 to the power I. So this is for this part. Similarly, you can get the same pattern over here as well. You have the first observation, you have current E1. For the second observation, you have the current E2, but there's also the previous period lag term, which comes with a coefficient, which is your A1. Similarly, for the third period, you have E3 current error term, you have the previous lag value of disturbance term, and you also have the two previous lagged disturbance term as well with the coefficient A1 to the power 2. So you can easily verify that this will have a pattern which can be written as A1 to the power I epsilon t minus I, where I goes from 0 to t minus 1. So the tth observation on this sequence can be written as A0 Is this point clear to all of you?
Yes, sir.
Sure. If there's anyone who has any problem, please ask right now. Okay, all right. So now...
So could you just give us a minute to copy it down?
Yeah, sure.
Sir, one question.
Yeah,
So when we expanded it for the third term, we were getting something like a1 square e1 plus a1e, right? So
yeah,
we are taking it to be summation for t minus 1. But the next term that is getting multiplied with the error is a1, right?
yeah.
So shouldn't there be another a1? Matlab, like the first observation itself in the
Uh,
third expression.
यहाँ पे
Yes, sir. In the third expression, so this particular thing is a1, square e1 plus a1 e2.
yeah,
So like this t minus 1 is corresponding to this ith wala jo a1 raised to the power I likha hai aapne.
yeah,
So that will like correspond to the second term, which is a1 e2, right?
yeah,
So the first term which is getting squared, how is that taken into consideration? A1 square e1.
yeah. So here the lag will be 2, no? So I will
Lag,
be
yeah.
2. I will be 2. Current term is 3. So 3 minus 2, 1. E1 and A1 to the power 2.
And the first term then?
So I is equal to 0. There is no lag. So it will be
Acha,
just
okay.
epsilon
Okay,
3.
got it, sir.
Is this clear? How do we get to this value?
Yes, sir.
All right. So just look at this part, that this solution or this final sequence term, this yt is what? This yt is the current value of y, which has been expressed in the terms of the initial condition and the epsilon terms and these coefficients. But what if this y naught is not known to us? That is, what if this initial condition was not known to us? So we can go back and we can keep on iterating backwards. So when the initial condition is not known to us, still we can proceed ahead. Since in this case the initial condition was known to us, we stopped at this part and then we said then this precisely is the solution for the AR1 that we have. Now without initial condition we cannot stop at this point because this is not known to us. So I can simply substitute y naught in this case with a naught plus a1 y minus 1 plus epsilon 0 on the basis of the sequence. So I can write this. So now we are talking about when initial condition is not known. Let me just derive it and then we can find out the conditions for both of them. So in that case, I can write my current T as now y naught ke jagah I'll have this. If you simply expand this, so यहाँ से आपको term आएगा a1 times t times a naught, a1 to the power t plus 1 times y minus 1, a1 to the power t e naught or epsilon naught plus this term. So if you just notice this term a1 to the power t a naught, if it gets added into this summation, which is only for the t minus 1, so I can write this as similarly, here from this point, a1 to the power t times epsilon, if it gets added over here, here again the summation will become and only term that is left over here is your a1 t plus 1 y minus 1. Now, you can keep on iterating backward, let's say m number of periods for n number of periods, as large number of periods as you can. So if you just keep on iterating, so let me say that continuing to iterate this backwards for m periods. So on the basis of this generalization, I can write it as oh, and I come to this final part. Is this point clear?
So not very clear, sir.
Yeah. At which step?
So the step above the red line. Are you trying to find what will
ये
happen?
वाला, yeah. Go on.
Are you trying to find out what is going to happen before a certain time zero?
No, you see, I could have stopped at this step, Neil, because now I have got a solution which there is no trend component over here, so I can get a stable solution from this. Sorry, I can stop at this step because this is a coefficient term. These are the white noise process, and there only I have one term a1 to the power t multiplied by y naught, which is known to me. That is initial condition is known to me. So I can stop at this point. But what if this y naught is not known to you? That is, what if this initial condition was not actually given to you? How do you stop at this point? Because there is no way you can get the initial condition or initial sequence of this time series variable.
All right, so if we don't have y naught, what is the new information that we have?
We do not have any new information. What we do is from this, so instead of stopping here, we keep on continuing it, iterating backward. That is, from the equation, if I have this as y naught, I can get, y1. If I have y naught term, I can get to y minus 1, y minus 1 say y minus 2, y minus 2 say y minus 3, and we can keep on iterating it for the backward sequence. That's what we have done over here. That is, y naught can be replaced by, according to this equation, if you have t is equal to 0, this t, so 0 minus 1 will give you y minus 1. So y naught can be replaced here by this term, which tells you that you do not actually know y naught, but you can keep on iterating it backward. And then once you just expand this whole term, you can come to that yt can be written in the y minus 1 form. That is when you iterated one period backward from the initial point. So it can be generalized to be written as like this. And if you keep on continuing to iterate it backwards for another m periods, that is, you keep on going m period backward by using the same consequence, the final solution or the final point that comes will be this term.
Sir,
Haji.
on this last equation, I just didn't get the last term, a1t plus m plus 1 y minus m minus 1.
What is this? We are iterating it m period backward, right? So यहाँ पे मेरा y minus 1 था 0 से, that is हम एक period backward जा रहे हैं. If you are going another m period back, so this will be y minus m minus 1. यहाँ से second term will be y minus 2, y minus 3, and so on and so forth. So this term will be y minus m minus 1.
Yes, sir.
So that's what I have written. और ये a1 to the power t plus 1 था for the 0th sequence. When you have mth sequence, so it will become a1 to the power t plus m plus 1.
How is it plus 1 and not just t plus m?
Because you have t plus 1 in this. So we are generalizing from this step till here, no? We are coming from this step to this part. In total, we have t plus m periods.
Acha, okay, I got it, sir.
So for the tth period, you have t plus 1. So for the t plus mth, we will have t plus m plus 1.
Yes, sir, got it.
Now you see, there are two precise restrictions that we impose in order for this sequence or in order for this solution to be stationary. You see here in this part, if we want to get a solution for a time series or for a sequence, I want my sequence to be convergent, right? My sequence should converge to a particular value or to a particular point, because if it is a divergent sequence, I'll not get any solution. So in order for my sequence to converge, look at this term over here, which is your a1 to the power t y naught. So I want this term to converge first. That is, I want this term to go out of my equation. Because if this term continues, it has a trend, it has a time as its exponent, so it will keep on exploding. It will never come to an end. So what we say here is that if mod of A1 is less than 1, if mod of A1 is less than 1, so as you keep on increasing the sufficiently large number of time periods, that is, as t keeps on increasing, this a1 to the power 2 t will become smaller and smaller and smaller and smaller, and ultimately it will go out of your solution. So that divergent part of your solution goes out of the equation. So the first restriction that we have is your mod of a1 is less than 1. Is this point clear?
Sir, could you repeat it once again?
Yeah. ये जो term है a1 to the power t y naught, you can see for yourself if a1 is greater than 1 or either less than minus 1. You can keep on experimenting with this. As your t increases, this term will never converge, because it will become larger and larger and larger and larger. For positive values, it will keep on exploding in a unidirection. For negative values, it will keep on interchanging depending on positive and the power. So in order for this solution to be convergent, I want this term to go out of my equation. So I put a restriction, I put a condition that mod of a1, that is the value of this coefficient, which is attached with the yt minus 1, which is attached with the lagged value of y, the modulus value or the absolute value of this coefficient must be less than 1. Even if it is equal to 1, you still will be getting a divergent sequence. Is this point clear?
Yes, sir.
Right? Okay. Now, one more thing, if mod of a1 is less than 1 and if your m is sufficiently large, that is, if your m becomes exceedingly large, then this term a1 to the power t plus m plus 1, again the homogeneous part of the term I'm talking about, this is called homogeneous part of the difference solution, this term will approach 0. Now these two terms will become sum of an infinite geometric series, this part, So now this becomes sum of an infinite geometric series. I can, simply write for this as A naught upon 1 minus A1. Is this point clear? How do I come from this step to here?
Yes, we are basically adding powers of A1 square,
Correct.
A1 and onwards, and that becomes like the GP ka R value.
Correct.
And 1 over 1 minus A1.
Correct.
And
correct.
all of them are multiplied by A naught.
Yeah. So this becomes sum of your infinite geometric progression, which can be, the formula for infinite summation is A naught upon 1 minus R. That is the first term. First term here is 1, but all of them are getting multiplied by A naught. That's why you have A naught upon A naught term over here. Now this term can be written as right? Is this part clear? Is this step clear to all of you?
So does this mean that we will get a converging point which will be the first term, and then everything else will depend on the error?
Correct. Correct.
All right.
So now the first term precisely gives you that constant mean value for AR. It is independent of time, so that's why it's a constant value. Now look at this term. This is very, very important for you to understand, because the model we can easily, run on software, but उसको समझने के लिए ये स्टेप बहुत जरूरी है कि ऐसा हम क्यों करते हैं, ऐसा क्यों बोलते हैं कि AR process stationary है, MA process stationary, and so on and so forth. Now look at this term. Each of the error term is multiplied by this coefficient, right? ठीक है? And coefficient is attached with the power, which gets defined by the lag. But this A1 is less than 1. It means कि after the current period or after the current shock, each of the previous lagged disturbance term has a decaying effect on the current value of Y. Meaning what? That the current value of the observation is not that much impacted or affected by the disturbances which have occurred way back or a long period ago. And in order for the AR process to be stationary, it becomes necessary that the previous random shocks of the time periods should have a decaying impact, or it should decay over time. That is, it should not keep on lingering the current values. And you can verify in this example yourself that if A1 was greater than 1, in that case, what happens is that the previous random shocks or previous shocks of previous time periods, previous or lagged disturbances keep on influencing, or they have a permanent non-decaying effect on Y, which makes a data non-stationary because they are ultimately the random shocks. And they keep on impacting, they keep on affecting the current value of Y. And that's why this condition that mod of A1 should be less than 1, this is for an AR1 process. We only had first order difference equation. But when you move from first order difference equation to higher order difference equation, just for example, if we write an AR2 process, and similarly you can go on expanding till pth lag. So what it says is that if you move from first order difference equation to higher order difference equations, you'll have, so get these terminologies right, जितने भी lagged term with the coefficients होंगे उनको हम बोलते हैं homogeneous part of the difference equation. So as many orders of the difference equation, as many homogeneous solution of the system you will get. Now in order to, we are not deriving this here, but just to get to the terminology, in order to solve this homogeneous system of higher order difference equation, you find characteristic roots of the system. So for second order difference equation, depending on the discriminant value, you'll have two homogeneous solutions. Whether they are equal or not equal, that will depend on the discriminant value. And those solutions of the homogeneous part, they are called as characteristic root. So the stability condition or stationarity condition for autoregressive process of higher order requires that all such characteristic roots lie within a circle of unit radius. All the characteristic roots of the system, they must lie within a circle of unit radius. Within means they must be confined under the circle which has a radius of 1. It means even if any one of the characteristic root is equal to 1, you have a non-stationary process. And by non-stationary, what do you mean? That your mean and variance will keep on exploding. It will never converge. And यहीं से unit circle का जो concept है, यहीं से आपका one of the most famous tests of stationarity has been defined, which is called your unit root test, which precisely check for this. That is, for the univariate time series under consideration, are there any characteristic roots which are equal to 1? If it is, then your series is not stationary and you call it as a non-stationary time series. And if all of such characteristic roots, if you're talking about higher order difference equation, if they lie within the circle of radius 1, you say the series is a stationary series. But the unit root test has come from this part. We have not derived, so that's why I'm not going to that detail, but just get this idea behind that ultimately unit root test kya check karta hai? It tests whether the characteristic roots of the difference equation that we have in front of us, all such characteristic roots lie within a circle of unit radius or not. So AR1 process, AR1 के case में we simply get to this condition where we are able to say this, that if mod of A1 is less than 1, your AR1 process will be stationary process. But there are some very generalized rules for checking the stability conditions in higher order difference equation. That is when you have AR2, AR4, AR5 ARMA process, then there are basically some rules through which you can actually check whether the process, whether AR2, AR3, AR4, AR10, whatever lag at which you're talking about is a stationary process or not. And same thing gets generalized for ARMA processes as well. So I'll just write the rules. It is not necessary for you to remember them, but just understand them. So first is that in an nth order linear difference equation, a necessary condition for all characteristic roots to lie inside a unit circle or circle of radius 1 is that sum of all the coefficients is less than 1. This is a necessary condition. And the sufficient condition is that since, because these are coefficients, some of them positive, some of them negative, so a sufficient condition is if the mod value of these coefficient, the sum of these mod value of the coefficient is less than 1. So these are the necessary and sufficient conditions to check for higher order difference equation that you have in front of you, that sum of all the coefficients excluding the intercept term, always remember this part, sorry, excluding the intercept term, one second here. So sum of all the coefficients which are there, they must lie within the circle of unit radius. And this is precisely the stability and necessary condition for an nth order linear difference equation. Now, after having gone through this general condition, let us calculate mean variance and auto covariance of an AR1 process just to check whether AR1 process after imposing these stability conditions also is a stationary process or not. Precisely what I should say right here is that the stability condition that are imposed on these processes are same as, yeah.
I'm so sorry, could you scroll up for a while?
Yeah. और
हाँ सर, ये mainly देखना था, but sir एक और चीज, if you could just scroll up just a little bit. So sir, we are basically looking at all these terms, right? A1, YT1,
correct,
YT minus 1. So sir, assume that I just take a AR1 which looks like something like, sir, if you could write down with me.
Yeah.
Let's say YT equals to 100 plus 0.6 YT minus 1 plus epsilon T.
Yeah.
Right, so would this be a AR1?
Yeah, it will be a stationary process.
Okay, sir. So basically we're just looking at the 0.6 or what all are we looking at? Because you mentioned we're looking at multiple things.
Yeah, we are looking at only the coefficients which are attached with the lagged values.
All right.
ठीक है? तो जब आपका हायर ऑर्डर डिफरेंस इक्वेशन में मान लो इसी केस में सपोज यू टेक AR2 प्रोसेस, so in this case, to check whether the characteristic roots lie within the unit circle or not, what we simply do is we take the sum of these coefficients which are attached with the lagged values. If it is less than 1, it gives a necessary condition. If it is more than 1, your series is, or your sum of at least one of the characteristic root is not equal, or is not is equal to 1. or greater than 1. This is what you conclude from this.
So out there it is given that sigma of AI
Yeah.
is less than 1. So sir, if we have a case of minus 1.1 and minus 1.1 as
Yeah.
A1 and A2,
Yeah.
that technically should not be a converging series, right?
Minus
Minus
come again?
1.1. So A1 equals, so YT equals to 5 plus minus 1.1 YT minus 1 minus 1.1 YT minus 2.
Yeah.
So sir, here the sum is obviously less than 1. The sum
Yeah.
is minus 2. So that is, but sir, we are not, it is clearly not a stationary one, right?
You see, the sufficient condition, in this case, if you actually add them up, it is obviously less than 1. It becomes negative. Then check for the sufficient condition. Mod of them, that is, since some of them positive, some of them negative, if the absolute value of these coefficients are less than 1, then gives you a sufficient condition. If it is not, then basically you are having a characteristic root which is, which does not lie inside the unit circle.
So and also sir, one more question, sir.
Yeah.
If I have one something like YT equals to 5 plus 0.YT minus 1 plus epsilon, which is an AR1.
Yeah.
Out there we can say it's stationary.
Yeah.
But the next case where we have 0.8 YT minus 1 and 0.8 YT minus 2, that becomes non-stationary, right?
Correct.
All right.
ठीक है? Is there anyone else? No? Shall I go ahead then?
Yes, sir.
All right. So now, these are the stability. Once I give you the notes, I'll give you at least one or two example of second order difference equation characteristic root कैसे find करते हैं. But precisely we don't need to do it on pen and paper anyway nowadays. But it is necessary for us to understand these conditions. Just by looking at the difference equation, can you actually come out and say, whether the series is stationary or not? That's why these two conditions we wrote. All right. So after having read this, let us talk about mean variance and auto covariance of an AR1 process. अगर वो stable है तो वो stationary होता है कि नहीं? So let me write this AR1 process. So your AR1 process is and we just saw the limiting value of AR1 process is this, right? By the way, can you also notice one thing, that limiting value of an AR1 process is the same as that of a moving average of infinite lag? Isn't it? This is a moving average term, right? Guys, are you there with me?
Yes, sir, but we can't understand, sir, this part.
ये moving average ये समझ में आ रहा है? This is that XT sequence.
Yes, sir.
Right? And this is what? This is the limiting value of an AR1 process.
Yes, sir. It's written above, sir.
Correct? So limiting value of an AR1 process converges to a moving average infinity. So you can also think it like that, limiting value of AR1, or you can say the solution of an AR1 process is basically a representation of a moving average of infinite terms.
But sir, in a moving average, we can have different values, different coefficients for different error terms, right?
Here also we have different coefficients, no Neil.
But sir, they are different. But sir, here there's a very specific relationship between all of them, right? Where it is ai to the power of I.
But how is it different? See, these are the coefficients which are multiplied by these white noise terms. So any sequence which are made out of these white noise terms multiplied by a coefficient is a moving average process.
Okay, sir. Okay. Yes, yes, yes.
है ना? So even if the coefficients are same for almost, let's say, all the error terms, still it will be a moving average. So generally there are, couple of questions or couple of interview questions where it is generally asked that, how you can also represent an AR1 process into a moving average process. So basically this is the answer, that when you actually find the limiting value or the solution of an AR1 process, that is actually, so you can say the solution of an AR1 process can also be represented by a moving average infinite process. Anyway, so this point, I thought I should tell you about this. So this is the limiting value of Y or AR1 process. And I have to check whether this is a stationary process or not. So first thing that I need to find out the mean value of this Y. So you can easily find out that the mean value of this whole term will be expected value of this constant. So this will be constant itself. Expectation of summation of this term, expectation will be applied over all these epsilon. This is a white noise term. So this entire term will go to 0. And you can easily verify yourself that your expected value of this AR1 process will be A0 upon 1 minus A1. And since this is independent of time, so you can say for all t. Next is your variance of yt, and variance of yt is what? Variance of yt will be your yt minus mu ka whole square. And you can easily write it, yt minus mu will be only this term because this is your mu only. So yt minus mu ka whole square, it means all of this term ka whole square. So I can write this as epsilon t. I'll just expand this. Square. Now all these are variances term themselves. Expected value of ET ka square will be your variance of ET. A1 square times variance of ET minus 1. And similarly you can find out. So you can actually take out sigma square, which is variance of these epsilon terms out. And what you will be left will be your 1 plus A1 square, because already यहाँ पे term है, plus A1 to the power 4 plus and so on and so forth. And this will be sum of an infinite series, which can be again written as sigma square upon A upon 1 minus R. So 1 minus A1 square. Again, this is independent of time. So this will also be valid for all t. So this is variance of your AR1 process. And finally, you have covariance or autocovariance of AR1 process, which can be written as sorry, t minus है. All right. Now, since these are white noise terms, so all the covariance term of ET with ET minus S, that is, which are different, they will all go to 0. So the only terms which will be left will be your variances term, that is ET का कोई यहाँ पे term नहीं है, so there will be no such terms over there. Then you'll have et minus 1 will get multiplied by et minus s minus 1. So इस तरह करके you'll only be left with the variances terms, and once you just manipulate it a bit, you can simply take sigma square out. And again, this will become a sum of an infinite geometric series. So you can write it as and which is again independent of time. That is, it only depends on lag. So, this precisely shows that mean variance autocovariance of AR1 process, it is independent of time change. It is independent of, it is not affected by change of time of origin. And you can conclude that AR1 process after the limiting value, we are talking about the limiting value of the AR1 process, and limiting value is what? Your mod of A1 is less than 1. And also M tending to infinity is called, just put in words, what it means is that what you are precisely saying is that the data generating process has started long time ago. And that's why, as a researcher, you should always be wary when you are dealing with the time series observation. If the data generating process has not started a long time ago, imposing the this restriction of stationarity somehow distorts the information what is available with you. So always what you'll find is that any time series econometrician will will worry about the timeline of the data generating process. That is, if the data series is a slightly new series, again checking for the stationarity, because in that case M does not sufficiently become very large, so you cannot go to the limiting part of the value. So these two parts you should always keep in mind, that for an AR1 process, the coefficient which is attached with the lag value of y, that is lag value of dependent variable, it should be, first of all, the mod value should be, absolute value of that coefficient must be less than 1. And the second thing is that the data generating process must have started a long time ago. Because if you have a data which is generated from a very new process, then such a series may not be stationary. And just imposing these stationarity conditions will distort whatever little information that you have in front of you. So yeah.
So I didn't get the part. How have you gotten A1 to the power S?
You see, A1 to the ये correlation term है. आप actually देखो, 1 second. ET with ET minus S is what? ET minus S is nothing but correlation of the error terms, S period lag.
Yes, sir.
Right, and if if only depends, and if we are saying that these are white noise process, the auto covariances will only depend on lag. So जो ET minus S का होगा वही ET minus 1 ET minus S1 minus 1 का होगा, वही ET minus 2 का ET minus S minus 2 के साथ होगा. So the covariances term that the auto covariances term that you generate depends on lag, and all these coefficients, they themselves will get multiplied with each other. So if you actually see what happens here is that A1 to the power S, which again defines, because all of them are separated by a time period like S, and all of them gets multiplied by the coefficient themselves, that is A1 square, iska term, iska term, and ultimately these autocovariance of white noise कैसे निकाले थे? That is nothing but your sigma square times A1 to the power S. And उसके अलावा all these coefficients are also getting multiplied by this term. If you remember in the yesterday we got the autocovariance of a white noise process.
Yes, sir. We got y to the power s.
That y is your gamma, that is your covariance.
Okay.
है ना? तो उसको जब तुम देखो, that autocovariance is nothing but this part, sigma square multiplied by a1 to the power s. But apart from this, you also have these coefficients which get multiplied, right? Say, you think like this, these terms are expected value of et with et minus s plus expected value of et minus 1 with et minus s minus 1, and all the respective cross product will become 0 because they are not autocorrelated. So now this term will give you autocovariance at lag s, which is your a1 to the power s, sigma square a1 to the power s, but again they all are multiplied by their respective coefficients as well. So here you have a1 et minus 1, a1 et minus s minus 1. So here you will get a1 square term from this part. Again you have a1 to the power 2, a1 to the power 2. That's why you will get a1 to the power 4 with respect to et minus s minus 2 part. But har ek ka covariance same hai because it only depends on the lag. So if there is autocovariance of et with et minus s, which is expressed as a1 to the power s, same autocovariance will also be there for the et minus 1 with et minus s minus 1, because again they are separated by s lag. Et minus 2 ka et minus s minus 2 ke saath same lag. That's why you get this term.
Got it, sir.
Yeah. All right. So this was just to show that the AR model or AR process that we have is stationary after we limit all those stationarity conditions. एक और चीज I should just tell you here before we move to R for various commands. Which is your autocorrelation function. Though we had discussed about it last lecture. This is also called your ACF. इसका concept समझ लेते हैं, then we move ahead with the examples that we'll solve there. So autocorrelation function for an AR1 process we can easily find out. जो आपका autocorrelation at lag 0 होगा, or autocovariance at lag 0 can be written as sigma square upon 1 minus a1 square. Autocovariance at lag 1 can be written as sigma square a1 to the power 1 will automatically be so a1 upon 1 minus a1 square. Similarly, autocovariance at lag 2 you can write as sigma square a1 to the power 2. और इसी तरह autocovariance at lag s, which we just found out. All right. So once we have these autocovariances, I can easily get the autocorrelation, because autocorrelation is nothing but, so if I'm trying to find out autocorrelation at lag 0, it will be autocovariance at lag 0 upon autocovariance at lag 0, which is nothing but variance. So rho, that is autocorrelation at lag 0, will always be equal to 1. Autocorrelation at lag 1 will be autocovariance at lag 1 divided by the variance. Variance here in this case is your sigma square 1 minus a1 square, and autocovariance at lag 1 is precisely this whole term multiplied by this a1 term. So this and this will get cancelled out each other, so it will only be a1. उसी तरह आप देखोगे autocorrelation at lag 2 will be a1 to the power 2 a1 square, and similarly autocorrelation at lag s will be a1 to the power s. Now, if mod of A1, which we impose it to be less than 1, then how should autocorrelation function of a stationary series or of an AR1 model look like, or it should look like? You see, your autocorrelation is so these autocorrelations, they depend on lag, and if mod of A1 is less than 1, that is, so each of the autocorrelation at various lags, they are a power of this coefficient A1, and which is restricted to be, or which is imposed to be absolutely in absolute value less than 1. It means each of those additional autocorrelation values must decay out to 0. So an ACF of an AR1 process, how will you find it? That after, if you're just saying that this is my ACF and these are all the lags. So at lag 0, let me plot it lag 0 if this is value 1. So at lag 0, you'll have this ACF as 1. But after that, what you'll find is there'll be a geometric decay in all those. And finally, it will go out to 0. Again, it depends on the sign of A1. That is, if A1 is positive, you will have a direct convergence like this. But if your A1 is negative, what will happen is convergence will be there, but that convergence will be oscillatory in nature. And that oscillation will keep on dampening after, as lags sufficiently become larger and larger, because A1 to the power, that value will keep on getting smaller and smaller. So in the case of negative A1 or A1 having a negative value, your ACF of an AR1 process will, after this lag 0, if for positive it will be positive, for negative it will be negative, again positive, negative, and finally it will become smaller and smaller and it will just decay out. So this is how ACF or autocorrelation function of an AR1 model should look like. How you obtain this? You obtain this by getting the autocorrelation at various lags, and these autocorrelation, they are just a function of lag. They will keep on getting smaller and smaller, and they'll finally converge to if it is a stationary series, it will converge to 0.0 very quickly. That is, the longer period lag autocorrelation will have lesser and lesser significance. And that's why they should converge to 0 as soon as possible. So agar completely purely random hoga, purely white noise series hoga, uska ACF will look like that. After that, at lag 0, after that value 1, almost all other autocorrelation coefficients at various lags will be absolutely almost equal to 0, or even if there is some value that will be insignificant or statistically insignificant. So this is what ACF of a series tells you. And that's why if you are, checking a univariate time series and plotting the autocorrelation function of that time series, so the time series is stationary or not, you can, basically look at the ACF graph or look at this correlogram and decide whether the time series under consideration is stationary or not by looking at whether it decays to 0 at higher order lags or quickly or not. If it does not, then the time series under consideration is not stationary. It is a non-stationary time series, and if it does, then the time series under consideration is a stationary time series. Now there are many such other methods as well that we had just discussed, that is your Dickey-Fuller, ADF, KPSS, Phillips-Perron test, and so on and so forth. But ACF function, apart from acting as an indicator of a time series, whether it is stationary or not, it also helps in identifying the lag of a moving average process. I'll repeat. How many lags for a moving average part of, let's say, an ARMA model, or let's say pure MA model, if there's pure MA model. So ACF, that is autocorrelation function of an MA model, will give you the lag indication. अब इसका लॉजिक क्या है वो पहले let me just talk about PACF and then I tell you, how do we exactly say this point. So you see what happens over here is that even though in AR representation you do not have, so even in this representation when you write an AR1 process, you do not separately have those autocorrelation at lag 2 terms, but your autocorrelation definitely contains all those part. You see, in this AR process, YT and YT minus 2, which is what autocorrelation at lag 2, YT and YT minus 3, autocorrelation at lag 3, they are correlated, but they do not, this YT minus 2, it does not explicitly appear in the model. But if you're just calculating correlation between YT and YT minus 2, which is nothing but your rho 2, that is nothing but correlation of YT with YT minus 2. So when you're calculating this autocorrelation, this autocorrelation is equal to A1 square, and you can understand that this autocorrelation is equal to correlation between YT and YT minus 1 multiplied by correlation between YT minus 1 and YT minus 2. So what happens is that when you're just calculating autocorrelation at various lags, it also gets influenced by all, or it also gets affected by all the intervening values between the lags. So if you're talking about autocorrelation at lag 3, that autocorrelation at lag 3 is affected by the autocorrelation at lag 1, lag 2. So when you calculate autocorrelation function in an AR1 process, what it gives you correlation of the current value with the lagged values of the variable, but this correlation contains all those influences of the correlation of the intervening values between them. In contrast, there's this another statistic, or there's this another function which is calculated, which is called your partial autocorrelation function, PACF. So partial autocorrelation function kya karta hai, that if you're calculating partial autocorrelation function between YT and YT minus S, what it does, it eliminates the effects of all the intervening values between YT and YT minus S. That is, right from YT minus 1 till YT minus S plus 1. जितने भी इसके बीच में है, that is YT minus 1 से लेके YT minus S plus 1, the effect of all these correlation have been completely eliminated when you calculate partial autocorrelation function of YT with its lag. So the name should suggest when you're talking about partial, you're only talking about correlation of the current value with the lag value, whichever lag you're talking about, keep eliminating all other eliminating effect of all other intervening values which are between them. So if I'm talking about autocorrelation, partial autocorrelation function of YT with Y3, sorry. Let's say YT with YT minus 3. So if I'm calculating partial autocorrelation function, it only gives me the correlation of YT with YT minus 3 और बीच में YT minus 1, YT minus 2, ये जो दो intervening values हैं, इनका effect it eliminates. That's what PACF does for you in time series variable. So अब इसी same logic से you can easily find out that if I'm talking about an AR1 process, so AR1 process क्या है? AR1 process में बोल रहा हूं if I only have one lagged value of the dependent variable with me, I can easily get the y. I don't need, the previous lagged values. Even if there would be certain correlation of these lagged values, but they all are insignificant. They do not influence the current value of y. This is why it is an AR1 process. Otherwise, if second period lag value or 2 period before lag value also impact y, then you would have an AR2 process. So ideally, ACF of an AR1 process will decay geometrically over time or over lag. But what about PACF? That is the partial autocorrelation coefficient, if I'm calculating. Then PACF of an AR1 for lag 2 should always be 0. In fact, apart from lag 0 and lag 1, PACF of an AR1 process will go to 0 for all the lags which are greater than or greater than 1. That is, in other words, it is also said that PACF for an autoregressive P order cuts off at P lags. So in order to identify the lag length of an autoregressive process, we use the PACF of that value or of that variable. Because partial autocorrelation function of an autoregressive process will simply be 0 after the lag that you have taken. So if I'm talking about an AR2 model, PACF after lag 2, that is for lag 3, lag 4, lag 5, all the lags, it will be automatically 0. If I'm talking about an AR10 model, then PACF after lag 10, all of them must be 0. This is what it means. So in order to identify lag length of an autoregressive process, PACF helps, and इसका ठीक opposite, that is for a moving average process. For a moving average process, how do we write a moving average process? We simply write moving average process as summation of the white noise process. So for a moving average process, the ACF of moving average process cuts off that particular lag. So if I'm writing for a moving average of order 1, and then when you calculate PACF of a moving average, it will behave in the same manner as ACF did for autoregressive process, because all the previous lag of y will still be there. But if you look at the ACF function, that is autocorrelation function, since these are white noise term, and if I'm just saying that it is only that ET minus 1 which impacts YT, so ET minus 2, ET minus 3, all the other lag of the residuals must be absolutely not impacting Y. So ACF of a moving average process cuts off after lag of 1. So PACF, that is partial autocorrelation function, I write it here. Partial autocorrelation function gives you lag length of autoregressive process, and autocorrelation function gives you lag length of moving average process. So generally आपका अगर, if you're saying that I have an ARMA PQ model where AR is for pth order, MA is for qth order, then ideally PACF of an ARMA PQ model must cut out after lag P, and ACF of an ARMA model must cut off after lag Q. Now, this is just for interviews purposes, because there's this automated command on R, which is auto.arima, which automatically gives you whether you have to go for AR2 or AR1 or AR2 MA0 model or AR2 MA1 model. That is, in short, it also gives you the lag length of AR and MA process. That is your auto.arima function. So but just if you're asked how exactly we identify the lag length of an ARMA process, so always remember PACF AR process का MA process ACF MA part का देगा आपको lag length. ये क्यों कैसे behave करता है? So if I'm talking about an autoregressive process, the partial autocorrelation of the current value with the lagged value which is outside of the model, it should automatically be zero. And similarly, since we are dealing with moving average part, and we are, moving average is composed of those white noise sequences. And if we are just talking about moving average of order 1 or of order 2, then after that lag, all other lags must have almost insignificant correlation with the current term. That's why PACF AR process, ACF MA process. Is this point clear?
Yes, sir.
All right, so let us take a break of 20 minutes. अभी 4:10 हो रहा है. We start at 4:30, and then we, whatever we have done, at least in theory, we'll solve all of these on our software using the example from the book that I had sent you. ठीक है?
सर
Yeah.
सर एक्चुअली जो टाइम सीरीज है सर वो एडवांस इकोनोमेट्रिक्स का सिलेबस है सर नेक्स्ट सेम में सर, तो हम इसको अभी क्यों पढ़ रहे हैं सर? दैट्स व्हाट.
No, time series also is there as far as basic econometrics is concerned, and हम बहुत ही बेसिक चीज पढ़ रहे हैं, बिकॉज मे बी हो सकता है इन एडवांस टाइम सीरीज it might all be skipped, or it might not be covered in this detail, because assuming that these things are known to you. So that's why we are reading. All right, so we meet at 4:30, exactly 20 minutes from now. All right, we can start now. Guys, can we start now?
Yes, sir.
So I request you to please open your R Studio. Can you all see my screen?
Yes, sir.
All right. So what we'll do is we'll take one or two examples from the book that I had sent you. And through this, we'll just try to, first of all, understand how do we actually store the time series data. Then we plot them. We test for stationarity, seasonalizing, decomposing. We'll do all this. जो भी example है. So in order to do that, first of all, I want you guys, so the three data sets that I'll precisely refer to for this session will be, these are the website data. Basically, if you go to the website, what they've done is they've removed their time series data library and they have updated it as a package on R, TSDL. But somehow, I think whenever I try to install that package on this version of R, I'm not able to install that. So that's why I've taken the data from the the URL file only. Otherwise, if for any of you, if you're able to install TSDL R package, then you can easily, just the way we used to access data set from the voltage package, you can do that.
Sir, sorry to interrupt. Could you increase the font size from tools?
Yeah, sure. I'll do that.
And so what's the name of the package?
TSDL. TSDLR.
So it'll be under appearance.
Up. Okay. All right. Can you all see the screen now?
Yes, sir, much better.
ठीक है, और बड़ा करूं थोड़ा? ये ठीक है? Can you identify?
Sir, I think it's fine. I think it's legible right now unless anyone else wants it to be bigger.
All right. So what I have done is, so I have stored these URL file as con1, con2, con3. So these are actually time series data from a professor, a statistics professor at University of Monash. And earlier these data were available on his website, but now it has been transferred into an R package. So these are the three precise data I have done. So let me also just easily copy paste एक साथ वो अपने आप console ले लेता है. I'm just doing that. All right. So as I told you yesterday, whenever I read any file from the website or internet, precisely because I know the way we want a data set, it need not be always in that format. So I just use this read lines function, which actually read some few lines. जितना भी आप n को mention करो उतना line आपको वो बताएगा. So let me just, for the time being, let me read first file. One second. You see, I've just read first 3 lines of the con1 file, and you can easily see that the first 3 lines are not actually data. It actually is the description of the data. So, but I don't need it as far as my variables are concerned. Similarly,
So could you please just send the first 3 lines of the code so we can have the link?
Come again?
So could you send the first lines of code CON1, CON2, CON3 so that we can have the code, the link, sorry, so we can have the link.
Yeah, done that. Similarly, I do for con2, but you see this is data point right from first space, and let me do for third file as well. Again, this is a data set, so I do not need to do anything. That is, if I'm just using this file, and so if I'm using the first file, I need to skip first few lines. So that's how, and this is a data set which is the data set of age of death of successive kings of England. So I have skipped first 3 portions. That's why it said read 42 items. And you can easily see by the heads command, these are the, these are the edge of successive death of English kings. Next, what I do is I want to store this data set as the time series variable. So for that, I have run this. That is, I've called the TS function, which makes a data set to be a time series. Now, ideally, if you look at time series ka argument, what it says that the first argument is your data. So data here is my kings. You can have just start date, end date. अगर मान लीजिए आपका start यहाँ पे नहीं, next data में we can find it. So you can easily fix your start. So you can write start, and if it is a vector, you have to use the small c, that is concatenate sign before the vector. Then you can also have the end date. Frequency by default is taken as an year. That is, frequency by default will take as 1. But if you have a monthly data, you have to write, like say frequency is equal to 12. If you have a quarterly data, you write frequency is equal to 4. So, but I have this, and let me just plot this.
Sir, I'm very sorry, but I'm not understanding what exactly you're doing.
You see, ye kings data is from the first file. That is, I have stored that as kings. Now, what I've done through this step is, Neil, that I have converted this data file into a time series object. So in order to store a time series object on R, you call TS function. Okay?
So what is the, so I'm not understanding when we make it into a time series function, what is the benefit or the differences that happen is my question.
See, time series object आप store करोगे, then you can perform all those time series analysis. Whether stationarity test or forecasting. So you actually have a normal data frame, but you convert into a time series, meaning which now your one of the variable will be your time. It automatically assigns a time to the data that you feed into this function. So benefit of storing a data set as a time series, because all the analysis which are there for the time series objects, you can easily perform analysis on a time series stored object.
Sir,
हाँ जी.
in your King's code, what is scan and skip doing?
You see, what I'm doing is that, when I had used this read lines for the file one, that is con1, what you notice is that the first 3 lines are not actually the data set. So what I've done is I've simply called scan function. This is just a way of reading data into R. So scan of what? Scan of this data file, that is URL. And I have to skip the first 3 lines because that is not exactly the data point. So that's what I've done over here.
Okay, sir.
Yeah.
So just another question, is read lines part of some library?
Yeah, it will be part of library. And are you not able to get read lines?
Yeah, so it is saying that I could not find function read lines. So I'm going to guess it's part of a certain library.
Yeah. एक बार just check read lines. It should be एक बार just let me check read lines किसमें है.
So it's in the T series library, I think.
Okay. 1 second.
So I found my error, so.
मिल गया?
So the error was the L has to be capital, and the second problem was we have to remove the word file, like even how you have to remove the word file.
अच्छा. Yeah.
वो 2 error थे मेरे.
Correct. All right, yeah. Oh, plot.ts I did, but so this is the normal plot of. So you see, when I store this data set as the time series variable on the x-axis, automatically I have the time. So it assigns a time value to each of the observation. So you can see easily you can identify that more or less this is not a stationary data set. For first few kings, the age of successive death has gone down, but after that it has more or less, it looks like an upward trend after a certain time. But we'll check through the formal methods. All right, so this was the data set where I did not have any start date or end date as such. But you can the moment you see the TS function, it has all these arguments. So in order to just give you an example of how do we exactly write that. So for that, what I do is you just take this file. That is, you use the data set, which is number of births in a year for every month in New York. So I store that variable as births. Right, so I've got this births data. It does not have any line to be skipped, so I've not used skipped here. And let me convert this births as, so let me write it as BTS. So births times series. Remember this many squares use क्योंकि console. So this is my data set births. Now here I have monthly data. So by default time series जो TS function है वो frequency आपका 1 लेता है. That is for a yearly. So in this case, I'll mention my frequency by writing it as frequency 12. Then I also mention here my start date is, that is I start from the 1st January 1946. So that's why you have C, that is C for the vector because it's a vector of length 2. So 1946 is the year and the month is January. It starts from the January month. And you can easily specify the end date as well, but it will automatically take depending on the number of observations it has. So now you have this BTS, and just you can plot this BTS. So again, you get this.
Sir, even if we don't do .ts, it's giving us the same plot, sir.
Yeah, it will give. this is your number of births in every month for the year 1946 to 1960 in New York. You can easily see some pattern of seasonality over here. A particular month may you have troughs and then you have peaks and troughs. Sorry. So this data more or less looks like a bit of seasonal component is there. We'll do all this. I'm just plotting all these data set. And again, the next data set, which is for, it is a data set of a souvenir shop. So again, the data is your monthly collection. So same thing goes there. So I'm not repeating that point here. Now, what we generally do is, so let us just proceed ahead with using this King's data and to find out everything. Next thing that we do is we decompose our time series. That is, so before decomposition, first a few things you should keep in mind that after plotting the data, if if somehow you're able to identify a seasonal pattern, then your data has a seasonal component as well. But not necessarily all the data sets should have seasonal component. So if you are talking about decomposing a time series into its various components which is not seasonal, so in order to decompose a non-seasonal time series, we use this function, simple moving average, abbreviated as SMA, to smooth the time series. And the function argument is that you have to mention the order of moving average. So if you're, if you want a moving average of order 3, 4, 5, 8, 10, so you have to mention the order as well. So, and SMA function will be in your T series. There's this package called T series. Two packages you must install by now. One package is your T series, install.packages T series, and the other package is your install.packages forecast, small letter, FORECAST. So two packages you need to install. First is your T series, that is all are in small letter, T for train, T series, and the other package is your forecast, which we'll be using in some time.
Sir,
Yeah.
could you just scroll up to just show the previous graph code?
Yeah. You just click on the up arrow, you can easily get. Yeah. So you see, this is the graph that we have.
What is the second package? I'm so sorry.
Second package is Neil forecast, FORECAST. F all are in small letter. ठीक है?
So can you scroll up the console a little?
Yeah.
Yes, sir. 1 minute. Just a little down. Okay, sir. Got it.
All right. So in this data, you see not such seasonal pattern you can easily, you cannot actually find out. So more or less this looks to me a non-seasonal data. And plus also I had mentioned you this point that whatever model or whatever mostly test that we perform for our course, they all are examples of linear model. So you, whenever you are using any function to decompose a time series, basically what you are saying is that all these components are additive in nature, and that's how you have all these packages or functions to help you out. So for a non-seasonal time series, in order to decompose the data, we use the function SMA function, which is mostly a package in T series, I guess. So after installing the package, you call the package by function library, and you can use that. So let me call it here. it is in T series, but let me see if it is right. So let me give it a name, Kings 1. And what I want to do, I want to decompose it. So I'll use the function SMA. SMA of what? On what data? So the data is Kings time series. And I state the order here, depending on how you want it to be smoothed out. Must be library forecasting. One second, guys. This should be TTR times TTR होना चाहिए सर. Okay, you also install this package TTR in order to use SMA function. Ideally, it should be a part of a T series, but I don't know why it is not taking. It takes, but I think it's a part of T series. Anyway, you also install this package TTR, all are in capital.
Sir,
Yeah.
यहाँ पे जो n है n is equal to 3
Yeah.
जो कि वो moving average है.
Yeah, it gives you the moving average का order. So now you see somehow data is smooth, but again, I can use a bit of higher order to smooth it more. So let us try it n is equal to 5. Again, this becomes a bit more or less you can identify कि एक trend तो है that starting from here till this point the age of successive deaths have gone down, but after that it has increased. So let me just take higher. So sample says takes n is equal to 8. Let us take that as well. So after doing this, more or less you come at this part, which is a simple moving average of order 8. So more or less now you can identify that there is this discernible trend pattern. For the first few kings, the age of death have gone down, but after that it has more or less shown an upward trend. So one thing is sufficiently clear that your data is non-stationary. You can easily just plot ACF and kings. I had stored it as kings, right? So this is the autocorrelation function of your kings data set. You can easily find that after lag 0 you have autocorrelation at lag 1, at lag 4 also statistically significant. These blue lines are your confidence intervals for all these autocorrelation coefficient. Idea क्या है कि अगर ये even if there are certain autocorrelation coefficients at different lags, but if they are statistically insignificant, they do not matter. But you can easily see that it is a sign of an indication of a non-stationary time series because you have lag 1 autocorrelation and lag 4 autocorrelation to be outside this confidence interval band. It means these autocorrelation coefficients at lag 1 and lag 4 are statistically significant. And if it and you can easily see that it does not decay out to zero. Lags keep on coming after 15, 20, 15, 16 lags as well. So this is what you do. You simply check for this. So more or less a pattern, you can easily find out that the data series is not stationary. And just to smooth the data set, we did it with simple moving average of order 8.
So
Now, yeah.
you're using ACF Kings out here and not Kings TS time series. What is
Kings
and
Kings को मैंने Kings TS से सेव किया है क्या?
हाँ सर, आपने टाइम सीरीज सेव किया था तो फिर मुझे वो लॉजिक फिर से समझा नहीं.
अच्छा.
अगर आपने टाइम सीरीज अगर कर दिया ऑलरेडी तो
रुक जाओ फिर, लेट मी सी टाइम सीरीज. It still shows the same thing, Neil.
हाँ सर, बेसिकली माय क्वेश्चन इज दैट फिर टाइम सीरीज करने की ऊपर जरूरत नहीं होती ना फिर.
You see, this is for this data, because the data simply it gives you there are successive observation, it automatically picks like that. But अगर कोई data stored नहीं है time series object से, तो बहुत सारे analysis आप नहीं कर पाओगे उस पे. And that's why you need to store an otherwise object into a time series object first to be read into R as a time series object. उसके बाद आप उस पे various tests आप perform कर सकते हैं, because there are certain packages which will not work for any other object. So it's like if you're just यहाँ पे simple एक example था नील कि you just had successive observations, 42 observations थे आपके, इसलिए वो pick कर लिया ऐसे. But if your data frame is large, if you have more than one variable, and if you have not stored them as a time series, or if you have not made them a time series variable, so बहुत सारे analysis नहीं कर पाओगे. So it is always better to store them as a time series object and then perform these analysis. All right, so so for the date of birth, let me go back here. Yeah, it was plot.tsbts. Yeah, now for this data set, so apart from trend and irregular components anyway I cannot do anything with. So apart from trend and irregular components, there is some element of seasonality in this. And if you look at the data set, what you will find is that in month of July and August, the rate of births are a bit higher than all other months, and compared to some of the months in winter months like January, February, वहाँ पे आपको rate of birth थोड़े सबसे कम दिखेंगे. So more or less in a given year, the number of births per month shows a seasonal pattern, and the pattern is that roughly in the winters you have a very less number of births, and during the summer, mainly in the month of July, you have a peak number of births in a year. So more or less when you have a seasonal data and you want to decompose the data into its various components, that is a trend, regular, irregular and seasonal component. So in order to use that, we use the function decompose, and this is a function which comes from the package T series. So let me just call that. So in order to decompose time series, what I'll do is I simply add BTS components, and I'll use decompose. You can also use STL function. That is also that also gives you the same thing. It also breaks the times univariate time series into its various components. So by default, it will take additive if you do not mention anything. So, and since our model is additive, we are just not writing anything. So decompose BTS, and Just use plot BTS components, so it will give you the figures of all the components like this. So this is your original data, and this you can see the seasonal pattern. Peaks repeat, troughs also repeat at a given point of time. So this shows an element of seasonality in your data. This is the irregular part, and this is the trend component in the data. So you simply use the decompose function, and by calling the library T series, and you are able to decompose the entire time series into its various components.
So could you please show your console once more?
Yeah. One second. Yeah. I've done nothing. जो मेरा time series data है, जो मेरा file है, first I stored that as BTS components. Otherwise, you can easily use decompose BTS on directly there. I have stored that as a variable, and that's why I'm able to plot it as BTS components. You can also get this same thing by let's say I just want to get seasonal. So what I'll do is seasonal BTS components $sign seasonal. Let me just change its name. Season. So we give you seasonal. Now if you plot Cs, so you'll get this seasonal. इसी तरह आप कोई भी component लिखा सकते हो. इसे आप trend component, if you want to get it, you simply use the $sign and you can get the trend component. Now, so this was about getting the components of the time series. So after we know that there's an element of seasonality or trend in our time series, it means it makes our data non-stationary. So उसको stationary बनाने के लिए either we go for trend stationary process or we go for deseasonalizing. So idea क्या है कि अगर
Sir, I'm so sorry.
Yeah.
वो जो decompose है, is that a part of T series?
Yeah, T series.
Sir, when I'm selecting decompose, sir, वो stats package से pick up हो रहा है मेरा. Any idea how I can change that?
Stats package. No, I don't have any idea why it is doing that. Can you just call library T series function and then use that?
All right, so I'll try that.
हाँ एक बार try करके देखो. So after getting the seasonal component, I can easily get my seasonally adjusted data. And the idea is what? Up seasonal component. So you can easily, if you just write it will give you the seasonal component. So these are the seasonal component for each of the months for the year 1946 to 1960. So you have Jan until December. So what I do is, जो भी मेरा original component है, so original component is my BTS. उस BTS में, which includes all the components, I subtract the seasonal component and I get my seasonally adjusted data. So let me write it at BTS AD, just to understand that it is seasonally adjusted. You can have any variable. So BTS minus, I have used BTS components. Yeah. BTS components, and इससे मुझे seasonal हटाना है. So now if I plot BTSAD, it will give me seasonally adjusted data. So now you see the data is seasonally adjusted. Now there is no element of seasonality over here. That is, these troughs and peaks, they do not reoccur or they do not occur at fixed points of time. So you have deseasonalized your data. This is what you do. अगर इसे मुझे trend हटाना था, suppose in this case, what I do is I want to remove the trend part of my data. This is what the data will look like. It will still have the seasonal component, but the trend part will go. So if you are able to make a data stationary by just removing the trend, that is called as trend stationary process. And if you're able to remove, or if you're able to make a non-stationary data stationary by deseasonalizing it, that is called as difference stationary process. So differencing again is a technique through which you try to make a non-stationary data to be stationary. And it is the same differencing which becomes, if you are using an ARMA model, so before using the ARMA model, you must be talking about a variable which is stationary. And if the variable is not stationary, first you have to make that variable stationary. And if you are making the variable stationary by differencing it, that is called as difference stationary process. So if you are able to make a non-stationary data into a stationary data just by differencing it once, it is called as ARMA, that is ARIMA of integration of order 1. If you are able to make a non-stationary data after differencing it twice, it is called as integrated of order 2. So when ARMA model, when there is a process of ARMA which gets integrated, that becomes your ARIMA model. And mostly as far as linear model is concerned, we use ARIMA model for forecasting. And that's what we'll do for our purpose as well. But this is what the entire logic of ARIMA is. Now, again, you need not worry because this package forecast, it automatically gives you that how many number of times you need to difference your time series to make it stationary. So let me just give you an example. So what I want to do, I want to find out number of diffs for BTS. Yeah, BTS was there. So I have to find out कि कितना number of differencing मुझे चाहिए BTS को stationary करने के लिए. Otherwise, it's a very tedious task generally. That how do we exactly find out? So X BTS. It gets you 1. That is, you can make your data stationary just by differencing it once. So you did not go for that trial and error. It automatically gives you that differencing order. So this is about decomposing a time series. You can use STL function or decompose function. Decompose function is used when you have a seasonal. Yeah.
What is X here?
X is the argument named here. If you write NDFS and then you see the first argument is your X. So we simply name X here as that is the data you want to test on. So यहाँ पे मेरा data BTS था तो मैंने BTS किया and I got it. Similarly, you can just test it on and see whether you require anything. It again says 1. You can make your data
So is
stationary.
it equal to or minus?
It's equal to.
Oh, sorry sir, actually मैं देख नहीं पा रहा.
नहीं कोई बात नहीं. अभी दिख रहा है? All right, then. So after we have found out whether it is stationary, अगर stationary है तो well and good. You go ahead with building your model. Stationary नहीं है तो पहले आप उसको stationary करते हो. Stationary करने के लिए you need to find out कि seasonal component है तो पहले आप उसको deseasonalize करोगे. Trend component है trend हटा दोगे. And if still you're not able to make your data stationary, you look whether your data can be made stationary by differencing it, and then you go ahead with forming the model. Now again, the major point of contention is how do we actually decide whether it's an AR model or it's an MA model or it should be a combination of ARMA. So the best way is, earlier it used to be the trial and error, but now there's this automated command, which is your auto.arima function. So what I do is I simply say auto.arima on what? On BTS. So it will give me automatically, we had already just seen that, it needs to be differenced once automatically also to make it stationary. So it will be a ARIMA model of integration of order 1. So I just say auto.arima. It gives us these contentious models, these two models. So what I have is, it is an AR2 MA2 integrated of order 1 model that we get. Just for the time being, just ignore this SAR and SMA. I'll talk about this. But what this auto.arima function does, it automatically gives you the lag length of your AR and MA part of your ARMA model. And by the ndifs function, you can easily get whether it has to be integrated of order 1 or of order 2. Otherwise, in the earlier cases, it needed to be done manually, and then selection of the best model used to be there. Yeah.
अभी जो हमने ये करा था ऊपर में सीजनलिटी कंपोनेंट को हटाया था, वो उसको हमने BTS AD में सेव करा था ना सर?
या
तो अभी जो इसमें auto.arima पैकेज मॉडल लगाएंगे, वो BTS.AD पे लगाएंगे?
या it should be done on BTS AD.
Okay.
Yeah.
Sir, auto.arima does not remove all those components?
No, it will not. You see, that's why you have this seasonally adjusted SAR1 and SMA1 here. So mostly what we do is we ideally it should remove automatically, but let me just check once. Remove it. Let me just do it once here. Yeah, it does remove it automatically, because you can see when you apply auto.arima on BTS AD, it gives you a differencing of order 0 because it need not be differenced anymore. So yes, it automatically removes that. It should have been done. Yeah.
So what was the use of this NDIFF function?
Yeah, NDIFFs ये था dear कि आपको कितना differencing करना चाहिए in order to make a data stationary. उसके लिए this is an automatic, or automated function. That is, suppose you difference a data once, but your data is not stationary. Then again you difference it twice. So in order to skip that step, you can easily find out this ndifs on the time series that you have, and it automatically gives you that whatever number, if it's 1, 2, 3, whatever it comes. So it tells you that it is integrator of order 3 or of order 2. It means you need to difference it twice, and then you can easily run the auto.arima function.
Okay, sir. Thank you.
Yeah. So auto.arima, it removes it automatically. I'm really sorry. It should have been there like that only.
Sir?
Yeah.
So could you explain the output of auto.arima? What is AIC, and log likelihood BIC?
Yeah, I'll do that. Give me some second. Is this point clear?
Yes, sir.
All right. So just for the time being, just ignore this SAR and SMA. These coefficients are what? ये model क्या है आपका? Now, so if you are using this, or if you're estimating this time series using ARIMA model, it means you're basing your forecast using this. And this is also, by the way, called Box and Jenkins method of forecasting. Box-Jenkins method of forecasting. So AR2 means what? You have two lag values. So BTS at T is regressed on BTS at T minus 1 and BTS at T minus 2. So these are the coefficients of those, lagged values. MA2 is again that same thing, that you have moving average of lag 2. So you have ET minus 1, ET minus 2. 1 second guys, क्या हुआ? तो लेके कैसे जाऊंगा मैं? लेके जाने में नहीं बनेगा ना, ठीक है? Yeah. So MA1, MA2 are those coefficients which are there for the lagged value, that is ET minus 1 and ET minus 2. So, and associated with these coefficients are your standard error. Again, this is your standard error of regression. AIC and BIC, these are the criteria. These are called archaic information criteria and Bayesian information criteria, which are basically criteria to, test for the model. अगर आपके पास एक दो competing model हैं, then you use these criteria. And also Auto.ARIMA क्या करता है? So you see why it gives you automatically, because it competes against all other, various models which could have been a potential candidate, but it gives you the best model, a best fit model. That's what it says. So on the basis of minimum value of archaic information or BIC criteria, it gives you this model, which is the best model. So that's what AIC and BIC refers to over here.
So what is the range of the value of AIC and BIC that makes it a best model?
It's not about the range there. Basically, AIC and BIC, these are the information criteria which are based on the residuals of the regression model. And basically, these criteria actually penalize a model for having too many, variables. Ultimately, penalize a model based on the degrees of freedom. So there is no such range. You build, let's say you build two models, you calculate AIC for both the models. जिस model का AIC कम होगा, उस model को आप select करते हो. So it's not something. It will not be like a statistic which you can compare to a critical or value. It's just an information. That's why it is called an information criteria, and precisely because it is based on the residuals. So there cannot be a range defined for this.
Okay, sir.
Yeah.
सर
जी.
सर दो क्वेरी है. एक तो अभी इसमें वो कांस्टेंट टर्म नहीं है, तो क्या उसमें ऐड होगा या ऐड करना होगा हमें एडिशनली? एंड
या
यस
या गो ऑन.
एंड सेकंड थिंग इज दैट सर ये Auto.ARIMA मॉडल डायरेक्टली लाइक हमें योर मॉडल देयर आफ्टर कटिंग द सीजनैलिटी एंड अदर ट्रेन. सो अभी हमें ऊपर वाले जो मेथड्स हैं जिसमें हम सीजनैलिटी कंपोनेंट को माइनस करते हैं, वो सब नहीं करने की जरूरत है?
या So basically, Auto.ARIMA is an automated command which is there to actually estimate estimate a model for a time series variable, and which automatically gives you. So अगर आप यहाँ पे differencing का जरूरत नहीं था, so it would give you differencing of 0. एक और चीज precisely ये ध्यान में रखना कि that ARIMA. So that I stands for integration, and that is precisely of the differencing order. So and so basically you can say it's like it's a shortcut which gives you automatically कि आप कौन सा function और कौन सा model fit कर सकते हो for the time series variable that you have. And second thing is the coefficients mostly in such when you have the coefficients themselves are part of the particular solution of a difference equation, And as such, these coefficients do not impact any analysis of the regression. So they're not actually included over here. They're not actually mentioned also here. But when you actually go for the prediction part, then those coefficients, basically those, the intercept term is just like the level of the series. So as far as the prediction part, which is based on the ARIMA and ARIMA model, in that case it will be added, but it does not have any impact on our analysis. That's why it does not give you that.
Sir,
Haji.
so this auto-to-Tarima, since our model didn't have a trend, so it's just showing the seasonal component coefficients.
Correct.
And sir, it's not removing the seasonal components coefficient, but it's rather minimizing it, right?
What it does, you see, when you integrate a time series, and which is of order 1, it means ये automatically उसको difference करता है once and then makes it stationary. Because if it is not stationary, you cannot run an ARIMA function, or sorry, ARIMA model. Precisely this integration of order 1 gives you that. So what it says is that even when you had trend in your original time series, but when you differentiate once, it becomes a difference stationary process. That is, it becomes a seasonally integrated process of order 1. So you are making otherwise a non-stationary process just by differencing it once, and it becomes a stationary process. That's why it is called a difference stationary process. So it definitely removes that seasonality part. Otherwise, you cannot run ARIMA, or you cannot have a model based on ARIMA if you have a seasonal component.
So sir, what does the coefficients of the seasonal component represent?
These seasonal component?
Yes, sir. Which we obtained from the BTS ad, we still obtained the SMA1 and SMA2 coefficients.
Correct.
So what do they represent?
See, just for the time being, just ignore this. I'll come back to this later. These are different from what we obtain here. Seasonal component यहाँ से जो हमें मिलता है, that gives you, if you actually see this for the 2 months that we have and for the February month that we have. So seasonal component क्या बोलता है कि out of the total, or out of the actual value of the y that you observe, उस actual value of y का, whether it is 1.16, 1.17, this particular portion is explained by seasonal component. That's what seasonal does. So stationary करने के लिए you simply take this seasonal out, but जब तुम इसको फिर again forecast करते, you again add the seasonal component back to those predicted values. So just for the time being, just take this as it is. I'll come back to this.
And so here in the output, it's written 201 and 112. So what's 112 here?
Again, that's why I'm saying ki I don't know why it gives us for this as well. It definitely gives us seasonally adjusted SAR1, SMA1, but let me just come back to you on this. It should not have been given in this manner.
And so what about the log likelihood value which we have obtained?
See, log likelihood again is an estimator which is based on the principle of maximum likelihood estimators. So जो हम basically जो हम regression करते हैं उसका हम एक likelihood function निकालते हैं. Likelihood function is based on the idea of joint probability distribution of these y's, and then you take the log of that likelihood function, which is nothing but a log likelihood. So again, this is an estimator which again gives you an information on that for this particular model, this is the log likelihood value of the model, or of this particular example. So it's actually based on a function which is called a likelihood function. So in the maximum likelihood method, that is MLE method, we basically calculate these likelihood functions only. And then we maximize the likelihood function on the basis of those estimators. And that's why it is called the principle of maximum likelihood. वही log likelihood ये होता है. Yeah. Someone was asking anything.
सर इस पर्टिकुलर आउटपुट में यहाँ पे कोई भी सिग्निफिकेंस टेस्ट काइंड ऑफ आउटपुट नहीं है जिससे हम ये कंफर्म कर सके ये मॉडल सिग्निफिकेंट है या नहीं?
You see, this, since this gives you automatic model, so that's why there is no such test over there. But the best way to test whether your model is a best fit model or not, you simply run a ACF test on the residuals from the model. So you simply run an ACF or PACF test on the residuals of the model and just check whether these residuals more or less are white noise residuals or not. If they are, well and good. If they are not, then again you have to go back to the model. But since this is an automated model that we get, more or less you can treat that to be the best fit model for the data set that you have.
So just
Yeah.
for the ACF model, if we get that the residuals are basically significant, then we say that it's non-stationary.
Correct.
Even if one of the value is significant.
Correct. Yeah. Because if the residuals, see, if you have correctly fitted your model, then जो ET, जो epsilon आना चाहिए आपका, वो आपका white noise होना चाहिए, because that's what your assumptions are. And if those epsilon are not white noise, that is, if any of the autocorrelation at higher order lags are significant, it means it violates that assumption, and that's why the model is not a correctly fit model.
Okay, got it. So.
Yeah. Okay, all right. Can we take another example and then wind up for our lecture?
सर लास्ट क्वेरी सॉरी
Yeah.
जो अभी हमने ऊपर एसीएफ प्लॉटिंग करा था वो पूरे मॉडल का करा था या फिर हम एसीएफ प्लॉटिंग रेजिडुअल का अलग से करेंगे?
ACF plotting residuals का अलग से करेंगे, because now your residual will become the variable.
Okay, so सर अभी हम करेंगे यहाँ पे अभी.
We'll do it.
Okay, thank you.
All right. So in order to go for the next example, what I ask you to do is I ask you to install this package, which is your from World Bank data. So let me just. So install this package called WDI. Let me see if I've installed it. Yeah, it is already there. Now, just to see, yeah, here's my package WDI. This is a description file, and these are the different values that it has. So this is the World Development Indicators data. This is how the data set looks like. You have country, you have indicator. कौन सा indicator क्या actually बोलता है, and if you really want to search an indicator, sorry, you can easily go back to this WI search and you can find out from this. So do this, just explore this data set a lot. For now, just follow. So just in order to use this, let me call the library function. Now what I'm doing is I'm just using an example. I'm taking 4 or 5 countries, and I'm choosing the indicator per capita GDP, at current dollar and per capita GDP at constant prices. Or just for the timing, let us take only US only, so we need not worry that much. So I'm storing that data as GDP, WI. Now, so WDI, it gives us that this is what you have to, actually write as a function. So I'll pull this for, say, US. So let me write it as US. And then the indicator that I'm just taking is your per capita GDP. And by the way, you can, if you want to have multiple countries, you can simply have country as a list of vectors. Similarly, multiple indicators, you can have, all those list of indicators as well. So here I'm just taking per capita GDP, which is the indicator ny dot जो आपका यहाँ example है, that I'll just take here. I'll mention the start. So you just see your head. This is what we get. So ISO 2C is the country identification code actually. So United States का US होता है, India का you can search from IND. NY, this is an indicator, so you can actually give names to all these columns. So let us do that. You can give names for each of them. So that's why I'm writing as vector, because I have naming each of the first को मैं as it is रखता हूँ. Second is my country, so I let it be as country. Third, I want to name as per capita GDP. So let me name it as per capita. Per cap GDP. And then,
Sir, do we need first, second, and fourth column?
come again? No, you don't need. You don't need.
So we can remove them and directly store it as time series.
Yeah. You can do that. Now if you see GDP, it will show you this. So you can give, so basically names is a function through which you can actually give column names to your data frame, which is what I've done precisely over here. So now I have per capita GDP of United States from year 1960 and ending till 2001. And I want to, so this is not a time series per se, I want to convert it into a time series data. So for that, what I'll do is I'll take this as it is and I'll convert it as time series. So in order to convert it time series, I do not need these columns. So I want this per cap GDP and I want this column to be converted into time series. So what I do is, let me call it as, let's say, US. I want to call it as time series. And this is my GDP. I want the third column, first, second, third. So I simply third column. I've converted it to a time series. And let me say start is your minimum value of GDP, or let's say I should just start. We will take. So now if you just see this, ओहो, the data is inverse. रुको, इसको मुझे करना होगा because the data actually 2011 से उल्टा चल रहा है. That's why you get this part. So let me call it as start of minimum GDP per year and as max of GDP per year. Some mistake. Yes. Tab. One second. Here is give me Mr. Why it gives me start
Sir,
1960. Yeah.
if we use a negative sign in front of the data, would it just inverse the observations? Inverse in the sense like reorder it upward, downwards. For the year, if you put a negative sign in front of it, so does it just...
Saying I should put start minus 1960.
Yes, yes, sir.
I don't think it should work that
No,
way.
not for that, just the variable name. Because if the variable name, if we are taking from the last value, so would it, I'm asking, I'm not really sure, but I think like we can sort the data that way.
One second, just one second, guys. Hello? क्लास में हूँ दीदी. Why it is not taking? It should take from start.
So you could sort the data by year first and then do this.
That I'm just looking for anything that I can do right. Yeah.
Sir,
Anji.
are we just trying to reverse the data set?
Yeah, yes.
So
Yeah.
I think there is a function rev, rev.dataset, so that might work.
rev.dataset.
rev इन rev फिर उसके बाद कॉलम और कॉलम में जो भी जैसे यूएस डेटा सेट है तो यूएस बस.
Let me try that.
सर प्लीज स्टोर इट अगर कुछ गड़बड़ हो गया फिर डेटा सेट.
नहीं, it's fine. I'm just trying. I don't know if it works. Fourth column, so second, fourth. All right. So define as use C function here. Bind and all right. So we can see now. Yeah. So I can give names to it. T is a per cap GDP, right? GDP and yeah. Really.
Sir, I think same result I got it from that function.
Why it is not picking it? Why it should not be? Okay, let be just for a time being. So let me store it as time series variable. So I'm really sorry. Guys, did you get this step over here? Can you hear me?
Yes, sir, we can hear you.
Yeah, yeah. So you can see like since the data was from reverse, so I just sorted column 4 of GDP, column 3 of GDP because this is what I needed. Then I've just combined those two columns and I've created a new data frame which is this. Now let me just convert it into a time series variable. So it's 1 TS and I want to convert US as time series. It should do for me because more or less it's same. Why? Oh, it's not working.
But you can remove the year column, right? It's taking that as well.
Oh, yeah. No, 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 not here. Actually, it should be. Basically, it should be US one. Yeah, US का मुझे कॉलम 2 और कॉलम 3 चाहिए. ये दोनों चाहिए टाइम सीरीज में. I should have done this. I must mention start 1960 and 2011.
So it can be continued tomorrow, like this example is not clear.
What?
Sir, is it possible that we can continue this like tomorrow or some other day whenever you're free? Because this example is just taking long and we are not able to understand this.
Okay. Okay. Well, just give me 2 minutes. Let me just check something.
But take column 1, right? The GDP.
Yes, so you're storing it in a new variable, a new bona data frame. So
yeah. So just check for whatever we have done for this data set. So you can easily say there. Just give me 5 minutes, guys. I'm really sorry for this delay. So you can easily see there is, as far as per capita GDP is concerned over here, you can easily see there is an upward trend. So and you can easily check it by simply calling ACF function. So I'll simply run ACF function on this, and you can easily see that ACF of this time series does not go away that quickly, which somehow, and you can easily calculate PSAF as well, which somehow leads you to conclude that the data series is not stationary. Now, before we do anything on the data series, we must be able to series. So ideally, we can go for differencing or we can go for trend stationary process. ये सारा चीज करने के बजाय we can simply use the nDifs function. So let me apply nDifs over here. So it gives me that you need to difference this data set one time, and simply we can again calculate again estimate this time series using auto-ARIMA function. So apart from this, apart from checking for stationarity using ACF function, I want you to run a command where you can, or we can use different tests like augmented Dickey-Fuller test or Phillips-Perron test or KPSS test. And the command for that is stationarity.test function. That is again a command that you get from T-series package. So just try using different tests for stationarity for checking the stationarity of the series, and then we'll take this example in the next session. So I'm really sorry it got delayed and somewhere we got stuck. I've taken so much of your time as well. So I'll stop here. Before next lecture, what I'll do is I'll share with you the file for dummy variables and an example of time series, and I'll also try if I can send you one or two examples where right from setting up the regression model till model diagnostic we perform tests, so that that can be used as a complementary for all the things that we have done. So stop here. I start from this point onward in the next lecture. When is your tutorial, by the way?
So 30th.
30th. उसके पहले we are meeting on 28th and 29th, right?
Yes.
All right. So in the next two lectures, we'll try to talk about forecasting using ARIMA and some of the exponential smoothing techniques like Holt-Winters smoothing technique. That is apart from ARIMA, जो में auto ARIMA हम कर रहे हैं, तो उसकी वजह these smoothing techniques are used for the forecasting in the shorter run, which are called Holt-Winters smoothing method. So we'll discuss these two aspects in particular, and one lecture before our term end starts, that is 30th के पहले जो मुझे खत्म करना, उसके पहले I'll just have one lecture on model diagnostics for the linear regression. So this is the two topic that we'll discuss in the next few lectures. And after 30th, if time permits, if there are lectures, I'll introduce some of the concepts of simultaneous equation model, just an introduction, the methods of simultaneous equation like two-stage least square, if time permits and if you guys are free after that. So I stop here. I'm really sorry for taking up your times for so long, and see you on Monday.
Sir, I have a question.
Yeah.
Sir, syllabus for this particular tutorial is before time series, right?
Till what we have done yesterday.
So is it possible
Sir,
if you
can
can
we exclude the time series, please?
टाइम सीरीज हमने कल पढ़ा ही नहीं, सिर्फ स्टेशनरिटी पढ़ा है. सो इवन इफ आई आस्क क्वेश्चंस ऑन स्टेशनरिटी that might not be on R, you need to answer that on pen and paper if I ask.
Sir, what
Is
is the
that fine?
pattern of the exam then?
It will mostly be on R, but it might be a combination of R and pen and paper. But pen and paper में मुश्किल से 5 से 6 मार्क्स का क्वेश्चन होगा, and rest will be on R.
And sir, could you also send today's R file? I'm not able to.
Yes, sir. Please send this today's R code.
ठीक है, don't worry, I'll do that.
Sir, can we exclude this stationarity part if possible?
But why, Rahul?
Because sir, like too many things happening, sir, right now. So we are overwhelmed, like honestly.
Overwhelmed in my subject.
Sir, in the subject, and then there are other things that we are like, there are 4 other subjects that we are covering up this semester. And with respect to understanding, also we would have to give time to watch these lectures all over again. And the time is not permitting us to cover everything at once. So that is why I was concerned that if it is possible, if we can exclude stationarity part and can keep everything before that. Because we can any which way have to cover this in the finals, no? So like that time if you can ask.
Okay, I'll inform you.
All right, sir. Thank you.
Thank you, sir.
All right, thank you so much for being there, listening to me patiently, and see you next. Stay safe, guys.
Thank you, sir.
Yeah.